So, dear students, welcome to Loss of motion. Last class we were discussing about tension in a string. No, not like this one. This is not the string that we considered. We considered strings which will not elongate. Okay. Now, from that we are going to the next force, which is called normal reaction or the normal force. Here, normal means perpendicular. Normal means perpendicular. So, when two objects are in contact, when they are touching, only when they are touching, there will be contact forces. Like when my phone touches the pen, there is a contact force. This contact force can be resolved into one contact force parallel to the surface, another contact force perpendicular to the surface. Are you getting it? Two objects in touch, there is contact force, and the contact force can be parallel or it can be perpendicular to that surface. So, what is normal reaction? It is a contact force perpendicular to the surface, the area of contact. And this is actually indicates how strongly they press each other. Like when I touch the board, somewhere here, I am actually pressing it. So, perpendicular to the board, I am applying a force, perpendicular to the board, it is applying a force. This is called the normal reaction, normal force. Okay. If I press it hard, normal reaction will be more. But you do not have to worry about this kind of normal reaction, we have to worry about some other type of normal reaction. So, what is normal reaction? The contact force perpendicular to the surface is called normal reaction. It is sometimes written as N, sometimes RR. Now, see this, say there are two bodies here, they are kept close by, but they do not press each other, there is no motion, they do not press each other, So, we will say that there is no normal force here. No normal force on each other. They do not exert normal forces each other. But see, they are at rest on this surface, but the surface is producing. Surface produces normal reaction. They do not produce normal reaction, but the surface is producing a normal reaction. But in this case, what happens is that you are pushing M1, so M1 will push M2. So, in between them, there will be a normal reaction. So, here in this area, there will be perpendicular forces. This will apply force on that one, that will apply force on this one, that is a normal reaction. More than that, from the surface also there is normal reaction. Okay. Third one, a sphere is resting in some surface here. It is touching this point, it is touching this point. So, these 2 points, there will be normal reaction. And this is a rod or a ladder resting on floor and the wall. So, it is touching, wherever it touches there will be normal reaction. Okay. It is important to know how to mark the direction of this normal reaction. Careful. In all these cases, how I am going to mark the normal reaction. Okay. There is no normal reaction in between them, but from the surface on A, there will be a force acting in the upward direction. That is a normal reaction on A from the surface. Similarly, on B, there is a normal reaction acting. So, this is normal reaction on A from the surface. Normal reaction on B from the surface. Same amount of normal reaction will act on the ground, but we are not thinking about what is happening to the ground, we are thinking about what is happening to the body. Okay. In this case, there will be a normal force acting here. We call it as a contact normal force. Okay. This is normal force on B due to A. And backward direction, there will be normal force on A due to B. There is normal force here, normal force on B from the surface, normal force on A from the surface. Normal means perpendicular. Here, there will be a normal force here, there will be a normal force here, perpendicular to this area, perpendicular to this area, two of them. Here, the point of contact, there will be a normal force acting here, and here depends on the nature of the body, it will be perpendicular here like this, normal force, most likely. It depends on how the surface. So, wherever you touch two bodies, there is a possibility of a normal reaction. Okay. And we are not worried about the normal force on the floor, we are worried about the normal force on the body. Most useful situation is this. There is a surface here and there is a body resting. Okay. Now we know that this body will be pulled by earth. There is earth here, earth will pull it downward. So mg is a force acting on the body. Mg will be the force acting on the body due to earth. It's pulling down. Now the body will press on the floor. The body will press on the floor and the floor will press on the body. Okay. So I will say there is a normal force acting downward. If I call this a surface and that is M, this is a normal force on the surface by the body. And this one here is the normal force on the body by the surface. These two are action reaction pairs. This one and this one are the action reaction pair. Mg is the gravitational force on the body and the reaction will be acting on the earth here. Okay. But what we want is the forces acting on the body, not the forces applied by the body. There is a big difference in that one. We want forces acting on the body. So which are the forces acting on the body? I'll tell you. This is a surface. The surface will push the body upward. Surface will push the body upward. We call it as normal reaction N or R. That is a force acting on the body due to the surface. The force acting on the body due to earth is marked as mg. Understand that mg and N are not action reaction pair. They are not pairs. Mg is by the earth, N is by the surface. There is a big difference in that one. Fine. Now, if the body is not moving, suppose the body is not moving, you can see there are two forces acting on the body now. Which are the two forces? Mg is acting in this direction, N is acting in the upward direction. That is in equilibrium. If it is in equilibrium, then we will say that N and Mg has the same magnitude. In fact, I should be writing N is a force vector plus mg is other force vector. If you add the two vectors, you should get 0, which implies that the magnitude of the normal reaction should be equal to magnitude of mg. That's why we normally write N equal to mg. In this chapter, we will always write this N equal to mg. Where is N equal to mg applicable? For a body at rest on a horizontal surface. समझ में आया? For a body at rest on a horizontal surface, this is applicable. What is the normal reaction on you right now? You are on a surface, horizontal surface, okay, and you are at rest. Rest means your whole body is not moving. Maybe your parts are moving, but the whole body is not moving. So the normal reaction is from the ground should be equal to your weight, mg. Okay. So I think that part should be clearly understood. Why is this not working? So hereafter many times this will come handy. Every time this will be asked on a horizontal surface, what is the normal reaction? That is equal to mg. Okay. Second thing, on inclined plane at rest or in equilibrium, there is a body on an inclined plane and the plane is at rest. The inclined plane is at rest. This is sometimes called wedge or inclined plane or sometimes inclined. That is at rest. It's not moving. Now I think we should work out this. This is the inclined plane which is at rest, and this angle is called angle of the inclined plane, and there is a body on the top of it, and we know that the weight of the body will act in this direction. This is the direction in which weight will act. This is the direction in which weight of the body will act. But you know the body has a tendency to move in this direction. So what we will do is that we will resolve this. We will resolve this into two forces. One force in this direction, another force in this direction. You can see if this angle is theta, this angle will be equal to theta. Make a proper understanding. If this is theta, that is theta. Use geometry. Then this component near to the ankle, we know this component is called mg cos theta. And this component is called mg sin theta. Resolution of vectors on inclined plane. Now, this is the surface in contact. This wedge will push this body in this direction. This is the normal reaction on the block by the wedge. Wedge will apply a force in that direction. Of course, the block will apply a force in the downward direction. That is not what we want. We want the force is acting on the block. So, if I consider the block, then from the surface there is a force, and that force is how much? You can see that you look in this direction, the body does not go up or down in this direction. It may be moving in this direction, but not in this direction. So, in this direction I can say along this direction it is in equilibrium. Along that direction is in equilibrium. That means, see, best thing is that you look at the diagram, you tilt your head like this and look like this in this direction. So, there is an upward force and there is a downward force, they are balanced. So, we can see that N will be equal to mg cos theta. N equal to mg cos theta. On horizontal surface, N equal to mg. On inclined surface, N equal to mg cos theta. But condition is that along this line it should be at rest. In this direction it can move, but in this direction it should be at rest. Okay. So, I gave you two equations, N equal to mg and N equal to mg cos theta. So, I am writing that equation again, very important equations, because repeatedly this will come in questions. Where is N equal to mg? Answer, level surface, body at rest. Okay. At rest, or it can be even uniform motion, it should be in equilibrium. Okay. Then we can say N equal to mg cos theta. This is on inclined plane. It is on inclined plane. And see, the body can move in this direction, no problem, but it should not move in this direction. That's it. Even for the first one also, it should not move vertically up and down, vertical equilibrium. So, that is about a normal reaction. This is one question from the NCERT textbook. You have 10 1 rupee coins. Count 1, 2, 3. Counted from the bottom. You should count from the bottom. That is why I have marked those few blocks. This is the first one, second, third, 4, 5, 6, 7, 8, 9, 10. 10 coins. Each coin has got a mass m. So, each coin has got a weight. Weight of one coin, W equal to mg. Weight of one coin, W is equal to mg. Okay. Now, what is asked? The force on the 7th coin counted from the bottom due to all the coin on its top. Look at the 7th coin. This is the 7th coin. And how many coins are there on the top? There are 1, 2, 3 coins. So, the weight of 3 coin will press this 7th coin. So, answer to the question number A is very simple. The force on the 7th coin due to all the coins on the top is the weight of 3 coins on the top. It is weight of 3 coins, which are like 8, 9 and 10, and that should be equal to 3 mg. Okay. The force on the 7th coin by the 8th coin, that can be sometimes confusing. I think I'll do here. This is the 7th coin and the 8th coin is here. Now, 8th coin is applying a force on the 7th coin, that will be in this direction. This force is what they are asking. And what is that force? Is it only the weight of one coin or is the weight of all the other coin? See, 8th coin is pressing 7th coin, but 8th coin is being pressed by the 2 other coins. So, that force will also come. So, the total force here must be equal to weight of the 3 coin above. So, answer B, the force on the 7th coin by 8th coin is again 3 mg. Okay. Last one, the reaction of the 6th coin on the 7th coin. The reaction of 6th coin on the 7th coin. Okay, I'll do here 6th coin and 7th coin. This is the 6th coin and this is the 7th coin. And 7th coin is pressing 6th coin by a particular amount of force. Let us call this F. F7 on 6. And there will be an equal force which is F6 on 7. Oh, I am sorry, I just wrote it wrong. Okay, I think it should be done in a larger way. So, this is the 6th coin, this is the 7th coin. 7th coin is pressing, this is the force on the 6th coin by 7th one, and the reaction is force on the 7th coin by 6th coin. What is asked? The reaction of the 6th coin on the 7th coin is this force. This is how much is this? That will be equal to F67, and F67 means what? The total force acting on the 6th coin is the weight of the 4 coin above. So, the answer to the part C is the weight of 4 coins, which are say 7, 8, 9 and 10, that must be equal to 4 mg. All of them are normal reactions. Fine. Right. You can consider that if you consider the 7th coin, you can say in the case of 7th coin, if you consider 7th coin as the surface, there is a 3m resting on top. So, the normal reaction here must be equal to 3 mg, and the force acting downward should also be equal to 3 mg. Okay. So, please work out that question. Okay. Now, this is again a very interesting thing. It is called real weight and apparent weight, because we sometimes will not feel our actual weight. Okay, first of all, what is the weight of body? What is your weight? Weight is the gravitational force on a body. Weight is the real weight is the gravitational pull on a body, and gravitational pull on the body is always calculated using the equation mg. So, we can say W real is always m into g. Okay. This is always constant. This always acts on your body, whether you are moving, at rest, accelerating, decelerating, anywhere, this is always there on your body. But what is the apparent weight? Apparent weight means it is the weight that you feel. Weight that we feel. Feeling. Is there feelings in physics? People say there is no feeling in physics, but this is what you have to feel. When I stand here, I am actually standing on the floor here, okay, because you can't see my bottom here, okay, I am standing here, I feel my weight. I feel my weight. What is that? What is that weight? Sometimes if you go to a doctor will take your weight, right? So, he'll ask you to stand on the weighing machine, you'll stand on the weighing machine, you'll take weight. And sometimes you have you can have there is something called spring balance, you can hang a body on the spring balance and you can see the weight. Okay. So, weight apparent is the weight that we feel or the weight that we measure. Apparent weight is the weight that we feel or the weight that we measure, and this is either normal reaction or it is tension. It is either normal reaction or tension. If you are standing on the floor, the weight that I feel right now is the normal reaction. If I am hanging on a cable, the weight that I am feeling is the tension. The weight that you measure anytime, anywhere is the normal reaction or the tension, not the gravitational force. Important idea. Arey bachcho, what did I tell you now? The weight that you experience is not your weight. It is a reaction from the support. That means even your weight is not yours. Even your weight is not yours. It is from the support. Okay. I will give you one exercise which you should never practice. Never ever practice. Okay. This is like this. You climb on a top building. Take a weighing machine, a spring balance in your hand. So this is the spring balance, and connect some body here. The spring balance will give a reading. You have the spring balance, there is a body connected, and the spring balance will read something. What you need to do is this: you jump down with the same spring balance in your hand, the same body, and you are falling downward. When you fall downward, if you have the presence of mind, if you look at this one, this will go back to the 0 reading. Here it might have been giving you 10 kilogram reading, but here it gives you 0 reading. But understand that here this body is pulled by earth, here also the body is pulled by earth. So the pull of the earth, which is the real weight, is there, but the reading, which is apparent weight, is not there. Whenever you are in free fall, if you fall freely, then the weight is not experienced because there is no contact, there is no support. So understand, real weight is calculated as mg, but the apparent weight is not calculated as mg. This happens due to, I will give you situations. Okay. Assume that there is a surface, there is a body, m. This is the gravitational pull on the body. This is called the real weight. And the normal reaction from the surface is called the weight that we experience. It is called apparent weight. Okay. First point, if body is at rest, if the body is at rest, then we can see that N equal to mg, which tells you W apparent equal to W real. When do we see that apparent weight and real weight are equal? This is either when the body is at rest or the body is in uniform motion. If it is at rest or in uniform motion, real weight and apparent weight are equal. I am at rest, so my real weight is a normal reaction. That's it. But assume that this is accelerating in the upward direction. If it is accelerating upward, what will happen? If it is accelerating upward, then I have to write like this one. Second case, here it is accelerating upward. So upward forces must be more than the downward force. So upward force is N, downward force is mg, and that must be the accelerating force. I applied F is equal to ma. The body has an acceleration, m into a is nothing but upward force minus the downward force. Out of this, which is the weight that we feel? The apparent weight is N. N equal to m into g plus a, and this N is the apparent weight, and that is greater than mg. So can you ever feel more weight? Of course, when you are accelerating upward, you will experience more weight. Suppose you are going in a rocket, in the beginning the rocket accelerates upward, you will feel many times your weight. That is the second case. Now the reverse. What will happen if the body is accelerating downward? Then third case, downward force must be greater. Downward force must be greater. So that means mg minus n must be equal to m into a. And what is n? The normal reaction will be equal to m into g minus a. And we can see this is the apparent weight, W apparent, and that is less than the real weight. So will you ever feel lighter? Yeah, of course. If you are accelerating downward, you will feel lighter. You always experience this when you are traveling in a lift. When you are in a lift and you switched on, suddenly the lift goes up, and that moment you feel as if you are pressing downward. You getting pressed downward. At that point you experience more weight because the lift is accelerating upward. In this case. When you come down, or when the lift stops, you suddenly feel lighter for a moment. That is because the lift is accelerating downward. In the giant wheel, at the highest point, you always felt this. feel like this because you are suddenly falling down, so your acceleration is downward, you are feeling lighter in weight. You jump down anywhere from the top to the bottom, as long as you are in the air, you will feel no weight at all. I can carry a huge weight on my head and jump down without feeling its weight. But the moment I touch the ground, I will feel it, maybe more than its weight. Okay. So, these things will appear in questions in many cases. Weight in a lift. Weight in a lift, many cases. First one, condition is here, figure is here, reaction equation, conclusion, everything is here. What is it? What is the condition? Lift is at rest. If a lift is at rest, then the body's normal reaction and the weight will be equal, R equal to mg, apparent weight equal to actual weight or the real weight. When is it? When the lift is at rest. Lift is moving upward or downward with constant velocity. Constant velocity means no acceleration. Again, the condition is same thing, R equal to mg, apparent weight equal to actual weight. So, when do we experience same actual weight in a lift? When the lift is at rest or when the lift is in uniform motion. Uniform motion upward or downward does not matter. Lift is accelerating upward. I did that earlier, right? R minus mg equal to ma, R equal to m into g plus a, apparent weight is greater than actual weight. Lift is accelerating downward, you will get apparent weight less than the actual weight, same equation. Write the equation and study. Lift is accelerating downward at the rate of g. This, when do we accelerate downward at the rate of g? That is when you are in free fall. You are in free fall, then your acceleration is equal to g downward. Then we will write the you will write like a downward acceleration means you know the apparent weight is given by m into g minus a, and put a equal to g, that will give you m into g minus g, that will become 0. So, if you are in free fall, you will feel weightless. See, if you want to reduce weight, if you are worried about your body weight, if you think that you are an overweight, the best way of reducing it, no keto dieting, no K2 dieting, nothing. Just jump down from a tall building. Your weight will decrease to 0 immediately. Okay. That is called weightlessness. It is a condition of weightlessness. In every satellite, this is experienced. If you are in a satellite, you do not feel a weight. You can't drink water just like we do that here, because water goes into your stomach because of action of gravity, but in the case of a satellite, that gravity's effect is cancelled. So, water will not go in. If you want to drink water, you will have to put that in your mouth, maybe you will need a long stick to push it down. I am kidding, okay, not really, that is not the case. Weight is not experienced, but they drink water in a different way. Now, we have a question from NCERT. A man of mass 70 kilograms stands on a weighing scale in a lift which is moving upward with uniform speed, downward with uniform acceleration, upward with uniform acceleration. What would be the reading on the scale in each case? What would be the reading if the lift mechanism failed and it hurtled down freely under gravity? We discussed all these equations right now, just now, and what are the equations for answer A? Answer A, it is in uniform speed, so actual weight, apparent weight, the reading of the machine. I say weighing scale will not read weight, it will read only that mass. Okay. So, in the first case, W apparent or the W read by the device equal to W actual. Okay. W actual means the weight should be mg. Weight should be mg, and what is m? M is equal to 70 kilogram, and g, if you take it as 10, that should be equal to 700 Newton. But reading, the reading will be in kilogram. How much kilogram? 70 kilogram. That is the point. The reading will be in 70 kilogram actual weight. In the second case, B, downward with uniform acceleration. Downward means we know apparent weight is equal to m into g minus a, and that is like a 70 into g is 10 minus 5. So, that gives you 350 Newton, and the reading will be how much? reading will be, for 700 Newton you read 70 kilogram, for 350 Newton this will give you 335 kilogram. Okay. Option C, moving upward with acceleration. So, there in the third case you will see if W apparent is equal to m into G plus A, which is 70 into 10 plus 15, sorry 10 plus 5, that is 15 into 7, that is 100 and 1050 Newton, right, 15 into 7, yeah, but the reading, how much is the reading? Reading will be 105 kilogram, reading will be 105 kilogram. And the last case, pray this will never happen in anybody's case, okay, because that's very dangerous. But nowadays the lift mechanism are so very good that if it breaks somewhere, that will get an automatic locking and this will come slowly to the next floor. You won't be in any trouble. But it is free fall, so we can say W apparent will be equal to 0. Reading will become 0 freely under gravity. Okay. So practice this equation, practice these questions. The same apparent weight concept can be asked in such questions like there is a rope, there is a man climbing, maybe there is a monkey climbing, there is a fireman climbing. In all these cases, such questions can come. See, they may give you the maximum force that can be supported by the rope, and you understand that if a man is holding the rope and stand still, if a man is holding the rope, after climbing the rope he is staying still, then the weight on the rope will be equal to mg, his actual weight. But if he is accelerating upward, then the weight of the man will be equal to m into g plus a. And if the man is accelerating downward, then his weight will be equal to m into g minus a. And if he is falling through the rope without touching it, then the weight experienced on the rope will become 0. So, 3 conditions. Tension, like see, when you apply a force on that one, that will act like the tension in the rope, and the tension will be equal to the apparent weight. Tension equal to apparent, that is the point that you need to remember. Tension in such cases, tension will be equal to apparent weight. And apparent weight will be given by all these equations. That's it. Tension will be greater than mg if the man is accelerating upward. If the man is accelerating upward, then the tension T equal to apparent weight is how much? M into g plus a. And this is greater than mg. Man is accelerating downward, then we know tension equal to, downward means m into g minus a, downward means m into g minus a, which will be less than mg, second case. Third one, man's acceleration is 0, acceleration 0 means what will happen? Weight will be equal to mg, so tension equal to apparent weight, and that will be equal to mg, and that's it, T equal to mg. So, you can use this idea to solve all questions about rope monkey problems. Okay. Dear children, just like the force in a string, the restoring force, spring also has forces like this. You have a spring like this, you elongate or compress, then the spring will apply a force in the opposite direction. Like imagine you have a spring, you compress it, then the spring will push you away. Or if you elongate a spring, it will pull you back. So, this is called the spring force. Spring force is the restoring force in a spring is called the spring force. I am sorry, this should be edited, this should not be tension, it should be restoring force in a this is not a tension. Restoring force in a spring is called spring force. Okay. For a spring, suppose there is a spring in the natural length. There is a spring connecting two bodies, and the spring is in the natural length means what? Natural length means not compressed, not elongated. Then there will be no force. But if you push the block up, like you elongate this thing. If you elongate this thing, what will happen? The spring will apply a force in the opposite direction. And if you compress this thing, the spring will push you. and this force is always given by this equation. F force is, spring force is equal to minus k into x. This means force is proportional to elongation or compression. You elongate more force, and the direction is what? If you bring the spring, if you compress it, the force is in the opposite direction. If you elongate it, force is in the opposite direction. So you can see that here the blocks are moving in the opposite direction. The spring force is opposite. Here the blocks are coming in this direction. So the spring force is again opposite. That's why there is a negative sign. F is proportional to x, spring force. Some of the important forces. We have another very important force in the next class. Okay, till then, bye.